Okay, now we're back again. So, video 10, section 2.6 on logarithms. And so we'll start this video by asking a question that comes up in finance a bit. The doubling problem. How long will it take $1,000, for example, at 6% compounded monthly to become $2,000, right? Or in general, if you're investing a certain amount, how long will it take to reach another amount? So, the doubling problem then, this is compound interest. Here's the compound interest formula. 2,000, we want in the future, 1,000, and we want to know what the time is, and the time is up in the exponent. And so, if we simplify it a little bit, we get this equation. 2 equals 1.05 to the 12t, right? What's t? That's what we want to know. How do you get a variable that's in the exponent? We haven't seen how to do this yet. And how do we do that? We use logarithms. So what's a logarithm? Well, logarithms are related to exponentials. So here's the graph of y equals 2 to the x. And we know certain things about the graph of y equals 2 to the x. And if you plug in x equals 1, what do you get out? You get out y equals 2. If you plug in x equals 2, what do you get out? You get out y equals 4. Right? That's that point. If you plugged in x equals 3, you'd get 8, etc., etc. But suppose you wanted to know, what should I plug into to get 3 out? Question mark. What's this number? And how do you find it? And the question is, can you solve that equation? 2 to the x equals 3. Can you solve that for x? Well, you can try, right? It looks like it should be around 1.5, right? So if you try plugging in 1.5, what do you get? We'll extend that down. You get 2.81. 2 to the 1.5 is 2.81. A little bit too small, so, maybe it's a little bit bigger. Maybe it's 1.75. Plug that in. You get 3.31. That's too big. And you can keep guessing, right? 1.625. Not guessing. Systematic guessing, I guess you'd call it. 3.08. So, it's got to be somewhere. Whatever this number is, it's got to be between 1.5, because that gives you 2.81, and 1.625, and that gives you 3.8. And so you can actually, at some point, nail it down a little bit and say that when you plug in 1.585, you get out 3.0078. So whatever the solution is to this equation, it's around 1.585. A little bit bigger than a half. Okay, so we have a solution. We have a name for this solution. Oops, running into my own writing here. Log base 2 of 3. Right? And what is a logarithm? In this example, and in general, a logarithm is a power. This is the number, it's about 1.585, that you raise 2 to get 3. It's the solution to this equation. So, 2 to the log base 2 of 3 equals 3. And that's sort of the definition of logs. It's trying to solve exponential equations, and we just give them a particular name. And they have a very useful collection, sorry about that, a useful collection of properties that can allow us to use them. So, a few facts about logarithms. Let's come down to this next picture. Here we go. So, If b is some number greater than 1, called the base, I don't know why that got erased, but if b is greater than 1, we call that the base. The solution, SOL apostrophe n, solution, to the equation b to the x equals a is x equals log base b of a. Okay, so it's a power. Here's a graph. What does the graph of y equals e to the x look like? This is y equals e to the x. This is y equals natural logarithm base e, logarithm base e of x. This is also written as ln for natural logarithm of x. This is the graph of y equals e to the x. This is the graph of y equals log x. And these are just reflections of each other. I suppose I should have done 2 to the x. That would have been a little bit easier. But if you look at the line y equals x, this line, this curve, y equals e to the x, and this curve, y equals natural logarithm of x, they're just reflections over the line y equals x. And why is that? Well, let's go back to 2 to the x for a moment. X, y equals 2 to the x. Well, if x is minus 1, y is 2 to the minus 1, which is 1/2. If x is 0, 2 to the 0 is 1. If x is 2, if x is 1, y is 2. If x is 2, y is 4. Okay. But that's going this way. But what logarithm does, it says if you give me the power, if you give me this number, the output, 2 to the x, then I want to know what the input was. So thinking about this way is log base 2 of x. So if we think about the table for y equals log base 2 of x, what do you get? Well, what's the log base 2 of 1/2? It's what number do you raise 2 to get 1/2? Well, that's minus 1. What's log base 2 of 1? What number do you raise 2 to get 1? Well, 2 to the 0 equals 1, so it's 0. If x is 2, what do you raise the base 2 to? And I should have used 3 so to have less 2's. What do you raise 2 to get 2? Well, the power you need is 1. The power you raise 2 to get 4 is 2. So the pairs minus 1 comma 1/2, 0 comma 1, 1 comma 2 that you get for the power function are just reversed to get the logarithm function. Oops, didn't want to do that. Sorry. So the graph of y equals 2 to the x would go through minus 1, 1/2, 0, 1, 1, 2, and 2. We'll put 4 up here. And it looks like this. Now the graph of y equals log base 2 of x, well, you take this point, x is minus 1, y is 1/2, and you use the 1/2 as the x-coordinate and the minus 1 as the y-coordinate. 0, 1, you use the y as the x-coordinate and the x as the x-coordinate. 1, 2, now we want something with x-coordinate 2 and y-coordinate 1. And you switch, this point is 2, 4, so instead of having 2, 4, we want 4, 2 for the logarithm graph. And so the logarithm graph looks like that. And so there's a graph of logarithm. So what we always want to know about our functions, what's your domain and your range? The domain is x strictly greater than 0. because if the question is, what power do you raise something to get another number, the answer has to be, hang on a second. The domain of log base b of x is x greater than 0, because if we're going to raise b to a power to get something, to get x, we can only think about the only numbers you can raise something, the only numbers you can get if you raise b to a power are positive numbers. The range, however, is all reals. So if you look at the graph is entirely to the right of the y-axis, but it goes all the way down this way and then all the way up there. Okay. So let's see how some logarithms work. So first off, so this is problem section 2.6, so dealing with problems 13 through 18, 27 through 30, 33 and 34. Can you calculate logarithms without a calculator? So what's log base 7 of 1? Well, this is asking a question. What power should 7 be raised to get 1? Well, 7 to the 0 equals 1, so the answer is 0. Log base 3 of 3. What power should 3 be raised to get 3? Well, 3 to the 1 equals 3, so log base 3 of 3 equals 1. 3 to the 1 equals 3. Log base 6 of 36. What power do you raise 6 to get 36? Well, 36 equals 6 squared, so log base 6 of 36 is 2. 6 squared equals 36. What's log base 2 of 1/8? Well, 1/8 we know is, it's an 8, it's a power of 2, but it's in the denominator, so that means we have a negative power, so it's a 2 to the minus 3. So we can say log base 2 of 1 over 8 equals 2, equals minus 3, because 2 to the minus 3 equals 1/8. And then finally, scroll down a little bit further. What's log base 9 of 3? Well, 3, right, that's square root of 9. What power is that? That's 9 to the 1/2 power. So that's my logarithm, right? 9 to the 1/2 power equals 3. So log base 9 of 3 is 1/2. Right? So if this is the base and this is the number, we want to know what power do you raise the base to get that number. 9 to the 1/2 is 3, 2 to the minus 3 is 1/8, 6 to the 2 is 36. And then other problems along the same line. This is asking now what's inside the logarithm. So the relationship between these three numbers, the base, this number on the right side, and the x, this to that is this. So this is asking, if you raise 5 to the second power, what do you get? So that's 25. If you raise 2 to the minus 4 power, right, which is 1 over 16, right, 2 to the minus 4 power. So we can rewrite this. Log base 2 of 1 over 16 equals minus 4, because this is 2, this number here is 2 raised to the minus 4th power. What's 81 to the 1/2? Right? Base raised to this power should be this number, so that's 9. Or log base 81 of x, of 9, equals 1/2. And then finally, again, log base 9 of x equals minus 1/2. Well, if you raise 9 to this power, what do you get? 9 to the minus 1/2. Well, that's 1 over 9 to the 1/2, which is 1/3, right? Because the square root of 9 is 3. So log base 9 of 1/3 equals minus 1/2. Okay. So some notation that we have, this is problems 57 and 59, sort of deal with types of notation. ln. This is the natural logarithm. That's actually French, so logarithme naturel. But this is log base e. And e is the number that we saw previously. So y equals natural log of x. That's the same thing as saying e to the y equals x. This is the power. The base is e, and that's the number. If we have log without any subscript, that means it's log base 10 of x. So y equals, if you just see log x without any subscript at all, that's the same thing as saying 10 to the y equals x. Okay, so problem 57, find those two buttons on your calculator, the log button and the ln button. And problem 57 in the book is really just, find those buttons, make sure you know how they work. So here's a problem. Log of x equals 2.48. And so we'll scroll down a tad. What does that mean? Well, log of x equals a number means that 10 to that number equals x. So x equals 10 to the 2.48. And you can get out your calculator and grind that through, and it's about 301.995. ln of x equals 1.74. Again, this is base e, so x is e raised to that power, e to the 1.74. And if you put that into your calculator, you should get 5.6773, if I can read my handwriting correctly. Okay, so problems 43 through 50 and 61 through 66 deal with the log rules. These have to be memorized. You will not be given this on a test or on a quiz. So what are they? There's three of them. Log base b of x plus log base b of y is log base b of x times y. If you have two logarithms added together, you can combine them into one logarithm by multiplying the things inside. And that's rule 1. Rule 2, very similar except with subtraction and division. Right. Two logarithms, one subtracted from the other, turns into a division, one logarithm with a division inside. And 3, the one that's actually the most important for us is log base b of x raised to a power. Means you can take the power out front as a coefficient. This is important for us because we want to solve for powers, if you remember the first problem. So this is sort of the most important of the three log rules for us. Powers can come out front as coefficients. Coefficients can go inside as a power. So those are the three log rules. And then we have a bunch of problems sort of how to use the log rules. So like this one, solve for x. What's this? Well, step 1, deal with the coefficients. Log base b of x is what? Well, coefficient of 4, that can go in as a power. 3 raised to the 4th power. Coefficient of 2/3, that can go in as a power. Log base b of 8 to the 2/3 power. And then this 2 can go in as a power, minus log base b of 6 squared. So all my coefficients can go in a power. Step 1, step 2. Simplify. So log base b of x, always write down the left-hand side of your equation. 3 to the 4th is 81. And then we have 8 to the 2/3. Well, 8 to the 1/3 is 2. 2 squared is 4. And 6 squared is 36. And then work your way from left to right, doing the addition and the multiplication. So we'll start with the addition. Log base b of x, there's my left-hand side. Two logarithms added together, I can make them one logarithm by multiplying the two things inside. And then step 4, we simplify again. Right? 81 times 4 log base b of x equals log base b. 81 times 4 is 324 minus log base b of 36. Great. And now we just have the subtraction to deal with. Log base b of x is log base b of, well, subtraction means take the two logs, turn them into one log, and divide the two things inside. That's a 4. 324 over 330 over 36. And then the next step is simplify again. Log base b of x is 324 over 36, which is 9. And then finally, if two logs are equal to each other, then that means the thing inside has to be equal to each other. So x equals 9. There we go. Not too bad application of the log rules. Start with the coefficients, bring them inside, and then deal with the additions and subtractions. Okay, here's another one. Oops, a little too far there. Log of x plus 2 minus log of 2x minus 1 equals 1. Okay, note, no base there, so what does that mean? We have base 10. Right? So this is log base 10. This, not a log, right? This is log of something, this is log of something, this is not log of something. So we need to turn that into log of something. So 1 equals log base 10 of what? What is that? Well, this is base 10 again, right? So x must be 10 to the 1. Right? Or 1. So what do we have? Well, I have two logs subtracted, so I can make that into one log by dividing the two things. And I can rewrite my 1 as being log of 10. Right? Because 1 equals log base 10 of x, which means x equals 10, so 1 is equal to log of 10. Great. And so now I can get rid of the logs, and I have that. And that's just a straightforward problem to solve. Multiply both sides by the 2x minus 1. Distribute, bring this 10 over, bring this x over. So what do we get? We get 12 equals 19x, or x equals 19 over 12. Are we okay? Well, we have to be careful. No negatives in logarithms. That was the domain rule, right? Well, that's what a domain means. What can be put into my logarithm? Well, we can't put in any negative numbers. So if we plug in 1912s into our original equation, do we get a negative number inside of a logarithm? Well, we get log of 19 over 12 plus 2 minus log of 2 times 19 over 12 minus 1 equals 1. This is positive, so we're okay. This will be 38 over 12, and so that's also bigger than 1, so that's positive, so we're okay. So you have to check your answers if you're going to put an x back into a logarithm, because if it makes something inside a logarithm negative, you can't use it. But here, x equals 19 over 12 is a solution. And we'll see cases like this one where that's not. Solve for x. ln, that means we're dealing with base e for both of these. This, we've got ln here, this is not an ln. So, ln of x equals to 1.791759. Or, how do you solve this for x? Well, this is base e, right? So e to this power has to be equal to x. And if you grind that out, e to that is actually equal to 6. So, our equation is log of x plus 3 times x minus 2 equals natural logarithm of 6. So I converted this number into a natural logarithm. Plus means multiply, combine into 1. Now I've got ln on both sides, so the insides must be equal to each other. X squared plus 5x, oops, not plus 5x, sorry, plus x minus 6. If you FOIL this out, you get a 3x minus 2x is my plus x equals 6. Subtract a 6 from both sides, because if we're going to solve a quadratic, we need a 0. X squared plus x minus 12 equals 0. This we can factor. X minus 4x plus 3 equals 0. And I think I got the signs wrong. X plus 4 and x minus 3. There we go. So, x equals minus 4 or x equals 3. Always check. Right? Our equation is, just to rewrite this a little bit, log of x plus 3 plus log of x minus 2 equals, well, it's log of 6. Plug in x minus equals minus 4. What do you get? Natural logarithm 4 minus 4 plus 3 is minus 1, plus log of minus 6 equals log of 6. That's bad. Right? Can't have negatives inside of a logarithm. So x equals minus 4 is not going to be a solution because it doesn't work in the original equation. What about plug in x equals 3? That's a minus 4. You get log of 6 plus log of 1 equals log of 6. Yes, right? Positive there, positive there. So this is a solution. That is not. Note that log of 1, right? What power do you raise e to get 1? Well, that's 0. So this is just 0, and you get log of 6 equals log of 6. Okay, so when you're doing these log problems, make sure you check your answers by plugging them back in. Make sure you don't get any negatives. And now we see why logarithms are particularly useful for solving equations when you have an exponent. So we don't have on your calculator a log base 3.78. You only have log base 10 and log base e. So to solve this, what can we do? We appeal to the log rule that says if you have log of something raised to a power, the power can come out front as a coefficient. Right? And so at this point, this is a number, log of 7. It's a little less than 1. This is a number, log of 3.75. It's also less than 1, smaller than that. So, what is x equal to? Log of 7. And then 5 times log of 3.75 goes in the bottom. This is a number you can calculate using your calculator. This is a number you can calculate using your calculator. 5, you know what that is. So you can plug that in, divide through, see what you get, and it should be 0.292674. This is done using log base 10. Does it matter whether you use log base 10 or log base e? Well, try it out. Take natural logarithm, 3.78, and these should all be 8s, shouldn't they? To the 5x equals natural logarithm of 7. Remember, it's an equation. You got to do the same thing to both sides. So if you take log of one side, you got to take log of other. Now the 5x, using our laws of logarithms, can come out front. And we get 5x times natural logarithm of 3.78 equals natural logarithm of 7. Again, this here, that's just some number. You can calculate it on your calculator. This is some number. You can calculate that on your calculator. So x is this number, natural logarithm of 7, divided by 5 times natural logarithm of 3.78. And all that is, again, 0.292674. Doesn't matter whether you use natural logarithm or log base 10. I use natural logarithm because, well, I'm a mathematician, and base e is much more useful for mathematics than base 10 is, but you can use either one. Okay, and so now we can return to our interest problems, and problems 79 through 84 are all like this, right? They're all considering things that are accounts that start at a base amount and go to another amount, and you want to know how much time it takes for the account to increase by that much. So, how long will it take for $1,000 at 6% compounded monthly to become $2,000? And so we use the compound interest formula. 2,000 equals 1,000 times 1 plus 0.06, that's my interest rate, over 12, compounded monthly, that's 12 times a year, to the 12t. You divide both sides by 1,000, that gives you the 2 on the left side. 0.06 divided by 12 is 0.05. 1 plus 0.05 is 1.05 to the 12t. So what's t? Well, now we know how to do that, right? We take log of both sides. Log of 2 equals log of, I'm using natural logarithm, 12t. The 12t now can come out front because it's a power, and the log rule says powers can come out front as coefficients. This is a number, this is a number, so we can solve for t. It's the number log of 2 over this 12 times log of 1.05. And what's that equal to? 1.183892. Right, it's about a year and 2 months at 6% compounded monthly for it to double. Okay, so that's basically it about logarithms. This kind of a problem is mostly why we're interested in logarithms, so that you can actually solve them and figure out how long it takes your account to go from a particular amount to another particular amount. And are we done? Oh, no, we're not. There's a little bonus video, a little history about logarithms. These were invented around 1620 by a guy named John Napier. When I was a kid, this is what we would see, a table of logarithms. How do you read this thing? Well, this is x, this is decimals, and these are the logarithms in here. So if we look at the line for 15, right, they say it's log base 10. So log of 1.5 is 0.1761. So you can look up your logarithms there. And these were actually really useful because what you could do with logarithms, oops, we'll just write on the side here, is can you multiply 152 times 392? Right? And you know how to do that. You can multiply numbers. But note that 1.5, if you go scientific notation, 152 is 1.52 times 10 squared. 392 is 3.92 times 10 squared. So this is useful. What's the log base 10 of 152? Well, it's the log of this whole thing, but that's a product, right? So that's going to be log of 1.52 plus log of 10 squared. So log of 1.52 plus the log of 10 squared, that's just 2. Because this is the power, right? Remember, log is the power you raise 10 to get 10 squared. That's 2. So, point 1 about log tables and why they're useful. You only need the logs between 0 and between 1 and 10, really, right? Because every number can be put in scientific notation. You need to find the logarithm of this, and then you add however many zeros you need to get the logarithm of 152. So the logarithm of 152 is the logarithm of 1.52 plus 2. Great. And you can look that up. What's the log of 1.52? The log of 1.52, we go to 15. Let me scroll up a little bit here. Right. So there's our 15. And we go over here. So this is 1.52 is 1818. Great. Likewise, log of 392 is log of 3.92 plus 2. And what's log of 3.92? Well, go to 39.5933. Great. So we'll leave that there, and we'll say we're trying to figure out what's 152 times 392. And what we found is that log of 152 times 392, what's that? Well, according to the log rules, that should be log of 152 plus log of 392. But we know what those are. Log of 152 is 0.188, 0.1818 plus 2. Log of 392 is 0.5933 plus 2. So whatever this number is, it's going to have a 4 as its power, so it's going to be 10,000 something. And if we add these two together, you get 0.7751 plus 4. And so then all you have to do is go back to your table and look for 0.7751. It's not on this particular table, but that is log of 0.7751 is log of 5.96. So what is this then? It should be about 5.96 times 10 to the 4th, or 596, and then you move over the decimal place. 1, 2, 3, 4. About 59,600. And it's actually 59,584. You can get the exact result if you had a more accurate log table, and there's all sorts of ways that people used to do this. But the point is that log tables made multiplying large numbers, which you need to do in astronomy, very simple and very fast, because you just had to look stuff up in the table and figure out what powers were. The slide rule, which was sort of going out of style when I was in high school, my generation was the first generation to actually use calculators in the classroom. The slide rule was a logarithmic table sort of as a machine. So, from about 1620 to about 1970, right, people calculated using slide rules and logarithm tables. They were really, really important for a long time. And of course, the second bonus video part, proofs of log rules. I know you've been waiting for this. The proofs of the log rules rely on two things. The first being that this, that log base b of x, that's the power you raise the base b to get x. So b to the log base b of x is equal to x. And the second thing we need to know is something from exponents. If b to the x equals b to the y, right? If two exponents are equal and the bases are the same, then x equals y. Okay, so to prove log base b of x plus log base b of y equals log base b of x times y, how do we go about proving that? Well, we say, we'll call this identity 1 here, and this is 2. So by 1, we know that x times y, well, x is b to the log base b of x. Y is b to the log base b of y. And if we have the same base, we can add the exponents. So that's log base b of x plus log base b of y. Also, by 1, we can write x times y in a different way. X times y is b to the log base b of x times y. Excellent. So, what do we have? This equals x times y, which equals to that. So what do we have if we put those together? By identity 2, b to the log base b of x times y equals b to the log base b of x plus log base b of y. Right? That's just saying this equals xy, which equals that. And so the log base b of xy, equals log base b of x plus log base b of y. Excellent. So there's the proof of that. The second one we can prove is the power coefficient one. My eraser is not working so well. There we go. To prove log of x to the r is r log base b of x. It runs the same way as this. We take the notation x to the r and we say, well, that's b to the log base b of x to the r, because anything is b to the log base b of itself. But if we are a little bit trickier about this, what do we get? We get x raised to the r, so the same thing here, is b to the log base b of x, right? That's just dealing with this thing in the parentheses, raised to the r. Now, if something raised to something raised to an exponent, I can multiply the exponents together, b to the r log base b of x. Great. And then finally, by part 2 above, what do we get? Well, this b to the r log base b of x equals x to the r, which is equal to b to the log base b of x to the r. And so what does that mean? That means my exponents have to be the same. R log base b of x equals log base b of x to the r. Okay. And we're running out of paper. Fortunately, the last one is pretty quick. Log base b of x minus log base b of y equals log base b of x over y. Well, we'll do this by using the two previous rules. Log base b of x minus log base b of y. Well, coefficient of minus 1, according to this, I can pull it inside as a power. Addition, according to the previous rule, that becomes a multiplication inside the logarithm. And y to the minus 1, what do we know about that? Well, that is down in the denominator, and so now we have the subtraction rule, gives us a division. So that's logarithms. Again, the most important one is the one that takes power.